Hello and welcome to the very first keynote of the very first PyMCon. My name is Chris Fonnesbeck, and I am delighted to be here today giving the keynote, and thanks to the PyMCon organizers for asking me to be here. I'm going to give you a little bit of overview of the PyMC project, specifically where it came from and what it is today and what we hope it will be in the future. So without further ado, I guess telling you what PyMC3 is a little bit redundant. If you're giving a talk or attending PyMCon, you surely already know what it is. But just as a little bit of background, the project itself started way back in about 2003. I'll give you a little bit of the details of that a bit later in the talk. It's a probabilistic programming framework, as you know, for doing Bayesian analysis. It's based on the Theano computational engine. And importantly, that is used to implement Bayesian inference methods, specifically what I would call next generation Bayesian inference methods, sort of the current state of the art. And there are now well over 100 contributors to the project. So, probabilistic programming languages are a thing now. The term is new, but probabilistic programming is itself not new. Really what we're talking about when we refer to a probabilistic program is really any program that is at least partially dependent on random numbers. That is, the outputs themselves are not deterministic. And that being the case, they can be expressed using any language that can describe a probability model, or really any language that has a random number generator. But that's probably overly broad to be useful. What we're really referring to here is a language that employs primitives that are stochastic. So just as we have integers and strings and floating point numbers, we can also think of a probabilistic programming language as having random variables or probability distributions that you can specify as simply as you would specify any other data type. And these stochastic primitives are used as building blocks and used to build Bayesian models. So we're using this to facilitate the application of Bayesian methods. And what this does is it gives us the ability to specify probability models at a very high level. So we abstract away a lot of the underlying machinery that goes into random number sampling and other forms of inference. And they can be as simple as a probability distribution that would be a distribution over values. So we might have x being a normally distributed random variable with two parameters, and we can assign draws from that to random variables. Or they can be something more complex, like a distribution over functions, so Gaussian process, for example, and we might use that object in turn to make predictions. And a really powerful thing that lets us do is to condition. So I talked a little bit about these being building blocks. If we have a large model with lots of parameters, it's often useful to be able to break that large joint model down conditionally and say, for example, as we see here, random variables that are Bernoulli distributed would be conditioned on some distribution that describes the likely values of those probabilities. So we have z given p. And we now live happily in what I might call the golden age of probabilistic programming. There are a lot of options these days. This here is just a a partial subset of available probabilistic programming languages based solely on the ones that I could think of, and those which had attractive looking logos. So we've got NumPyro in here. We've got Web People, Edward, Stan, which probably has the largest mind share these days in probabilistic programming. So, this is PyMCon, but it's important to remember that, probabilistic programming is much, much bigger than PyMC. And this is a good thing. Back when the project started, we didn't have this kind of choice, and it's nice to be able to implement Bayesian models not only in multiple packages but on multiple platforms, etc. So how do we get here? How do you go from an idea about wanting to build Bayesian models in Python all the way to what we have today, which is a sort of a medium-sized project with a large number of users and a robust community, and now its own conference. Well, you got to go all the way back to the year 2000 or thereabouts. This was when I was in graduate school. I'd just arrived at the University of Georgia, having done a couple of biology degrees. So my background is in biology, specifically ecology. And to that point, the only statistical package that I'd ever really used was SAS, and Bayesian methods were not widely taught in undergraduate or graduate curricula, at least in North America. The go-to package for doing Bayesian analysis at that time was something called WinBUGS, which still exists today, and it sort of provided the inspiration for PyMC. And looking back on it now, I built PyMC sort of out of frustration with WinBUGS, but really you have to give it and its creators a ton of credit, because it really brought Bayesian analysis to the masses. It was really your only alternative to coding these samplers by hand, and this allowed users that weren't necessarily computer scientists or really necessarily even statisticians to be able to build models to solve their particular problems, and it was fantastic. I mean, we're talking about the mid 2000s here, and we've got what we have here is a nice Bayesian dashboard here where we can set initial values and quantiles to track, and we could even watch the sampling occurring in real time. And better yet, BUGS was its own domain-specific language for specifying Bayesian models that was not unlike R. So this is a really simple random effects model, hierarchical model here, and you can see that it's quite concise and easy to read, and it made it really easy for people to specify models and it abstracted away all of the computer science and left the user simply to write down their problem as code. But it had its own limitations, of course, as all software does. It was, as the name implied, Windows only. You couldn't run it on other platforms unless you had a virtual machine. So I spent a great deal of time getting this to work on Wine so I could run it on Linux. You couldn't run MCMC on any sort of cluster. It was closed source. You couldn't modify or redistribute it in any way. It could really be a bear to debug. You would get these sort of stochastic error. Not only was the output stochastic, but the bugs were sometimes stochastic as well. These trap errors that were impossible, at least for me, to interpret, and you were kind of left in the dark as to how to solve some of the programming issues that would arise. Eventually, Bugs did become open source. There is a project called OpenBUGS, and it does run on multiple platforms. It is not well supported, even from the outset. There's really only one developer that spends about a third of his time on developing it, Andrew Thomas. And it really isn't, despite open being in the name, really isn't much of an open source project. And I had the pleasure of meeting Andrew at a meeting several years ago, and his quote was that OpenBUGS was open source only in the read-only sense. So the source code is not posted on any sort of public website, at least it wasn't at the time. And there wasn't really much interest in growing a community of developers around it. Even if you were inclined to contribute to OpenBUGS, the thing you have to realize is that it was coded in component Pascal. I'm not sure how many Pascal programmers are still floating around, but I'm not one of them. And there are a lot of sort of roadblocks or points of friction that would prevent users from contributing back to the project. For example, you need a proprietary Windows-only IDE to build it. There's no debugger in that IDE. The source code itself is not even plain text, and to this day, if you happen to run into a WinBUGS or OpenBUGS model online, you actually can't read that model. There are these ODC files that are binary, and makes it really difficult to inspect models that were built in the past. And the whole thing was abandoned by Oberon Microsystems several years ago, although there have been attempts to create open versions of Black Box Component Builder. So, as a graduate student slash postdoc in the early 2000s, who also happened to be trying to learn Python, started tinkering with building some of these samplers, partially in an effort to, learn this stuff, learn how to do Bayesian inference with MCMC sampling. And out of it came the first version of PyMC. My background, again, was as not only a biologist, but one of the first jobs I had when I got my master's degree was as a Java programmer. I'd learned Java on my own while traveling in Italy, and got a job doing Java programming. And so when I was learning how to do Python, everything that I was doing was very heavily influenced by my experiences with Java. So it was a very heavy object-oriented implementation of MCMC. And, the goal, again, was just trying to be able to build Bayesian models in Python. And the first version of PyMC, PyMC1, was really just a handful of classes and functions for doing Metropolis Hastings sampling. And this project was based on the numeric package. So this was pre-NumPy, where you had to make a choice anytime you wanted to use an array data structure as to whether you used the numarray project or the numeric project, and this was based on numeric. So this was really only intended for my own use and perhaps others in my lab at the University of Georgia. And of course, this was before the days of GitHub, but eventually it did find its way onto SourceForge, where other people discovered it and started to play with it themselves, and in particular, two other biologists, Anand Patil and David Heward, who were both much better computer scientists than I was. Joined the project. So there were now, rather than being a one-person show, it was a three-person show, and they completely revamped and expanded and refactored a lot of the code, and developed what became PyMC2, which is still available. And this was sort of the first version that I wasn't completely embarrassed to share with others. it includes a pretty much every statistical distribution you might need. At that point, NumPy had appeared, so it was switched over to using NumPy. Anand, who was studying applications of Gaussian processes himself, implemented GPs in PyMC2. It included convergence diagnostics and other niceties that weren't in the first version. The important piece was that it was based around essentially a set of Fortran functions that were compiled into Python using the really great package called F2Py, which allowed you to take Fortran functions and turn them into Python functions to improve performance. And in fact, if you look on GitHub now in the PyMC repository, it is actually identified as a Fortran project. So with a sort of a little outer layer of Python to hide all the unpleasant Fortran from its end users. This attracted a fair amount of interest from applied users, mainly in ecology and astronomy, places like that, mostly academic. The next major innovation then came when sort of what I referred to earlier on as the next generation of Bayesian inference methods started to be developed in the mid-2000s, and namely gradient-based MCMC or hybrid Monte Carlo. One of the issues that you would run into using PyMC or BUGS or whichever implementation of Metropolis Hastings that you might try is that for even moderately sized problems in terms of numbers of variables, the Metropolis Hastings or Gibbs samplers would get stuck. And so this is this slide is taken from a paper by Matt Hoffman and Andrew Gelman that established the NUTS algorithm, that published the NUTS algorithm, and it shows what Metropolis and Gibbs do for really a simple but large model. So these are marginal, two-dimensional marginal distributions of, I believe it's a 1,000-dimensional multivariate normal. So again, not a very complicated model, but perhaps a big one. And Metropolis and Gibbs sampling doesn't do a very good job of characterizing it relative to independent draws that you see there on the right. And that's because they use a random walk to try to explore a high dimensional space, and you very quickly run into trouble exploring that space using just a simple though general random walk methodology. And around that time, I'd read the blog post of a PyMC user named John Salvatier, who had come across gradient-based methods and kind of wondered out loud why these methods weren't being used. And I sort of shared his concern and question about this, and essentially offered to let him revamp the project to adopt these methods and implement them in Python. And initially he was hesitant because he didn't want to sort of refactor the existing code base to do gradient-based methods, because they're very different from the first generation methods. But I really gave him free rein, as Anand and David had essentially moved on at this point from the project. I essentially gave him free rein to create a new version of PyMC from scratch. And what he did was implement some of these methods using the Theano package. And I guess the main challenge to doing gradient-based MCMC is having a way of generating gradients easily and automatically. And Theano was and is essentially a deep learning library. It's a library for building mathematical expressions involving multi-dimensional arrays, which they call tensors. And it was initially developed for implementing neural network models. But John hijacked this infrastructure essentially to do Bayesian gradient-based MCMC. And what it allowed you to do was to construct a graph and compile that graph to, in the case of Theano, to C, which allowed you to do a lot of optimization, allowed you to run it on GPUs and other hardware, and importantly to do automatic differentiation. So here's just a very simple snippet of Theano code where a matrix is specified, and then we would transform, do an arbitrary transformation, an inverse logit transformation, and then take the gradient of it. So this single line of magic here is automatic differentiation in action. And so this was used as the building block for PyMC3, the third major version of PyMC. So this was again a complete rewrite of the PyMC code base using Theano and the NUTS algorithm, which is a auto-tuning version of Hamiltonian Monte Carlo or hybrid Monte Carlo, was developed as the default inference algorithm. Later on, several other methods were added, such as variational inference methods, courtesy largely of the efforts of Taku Yoshioka and Max Kucherov, that use optimization rather than sampling to do approximate inference. So this is kind of what we see today when you build a PyMC model, is the PyMC3 syntax. It uses a context manager to add variables to a model, and again, inspired by BUGS from a couple decades ago. It is a really concise way of identifying, or of specifying and fitting models, and I always liken it to a whiteboard, a virtual whiteboard of sorts, where in this example, there's essentially a one-to-one correspondence with every line of math to a line of PyMC code. So this is I sort of chose this example because it shows all of the different PyMC or PyMC types, or probabilistic programming primitives, if you like. So we've got, this is a acute gastroenteritis model, where we've got, we're trying to estimate the rates of AGE from observed cases. So you're trying to adjust cases using sampling weights. So you're estimating the probability of the observed cases, and then you want to use that in a transformed way as a Poisson rate parameter to estimate the underlying rate of AGE in the population. And so, again, the idea is that it should be just about as easy to code your model as it is to write it on a whiteboard. And then, having got that model, this is a different model, but same idea. For any particular model, you can run pm.sample, and PyMC will automate a lot of the decision making in terms of fitting this model. So it will auto assign a sampler for you. If all of your unobserved stochastic variables are continuous, it will choose NUTS, and it'll choose an initialization method and sample multiple chains automatically. And Thomas Vicky, one of the founding developers of PyMC3, likes to call this the automatic inference button. So you're just essentially in one line of code generating MCMC with all of the computer science and statistical details abstracted away. And there's quite a large leap in adoption from PyMC2 to PyMC3, and it is now pretty widely used in a range of applications. These are sort of the ones I could think of off the top of my head. Lots of epidemiologists using it these days. Chemistry, finance. I use it to do baseball modeling, insurance modeling, and so on. And the example here on the right-hand side is taken from a paper by a colleague of mine, Aaron McNeil, who is a marine biologist, and this is a model of a different type of outbreak than the ones we've been thinking about recently. These are outbreaks of crown of thorns starfish on the Great Barrier Reef, but the methods are similar. And more recently than that, in the context of COVID-19, the founder of Instagram, Kevin Systrom, and a developer, Thomas Vladeck, used PyMC3 to model the RT values, the basic reproductive or the effective reproductive number of COVID-19 across the various states in the US to kind of give a real-time idea of what the virus is doing in each state. And you can see this at rt.live. So it's just one recent application of PyMC3 kind of in action. We're now a sponsored project under NumFOCUS, which we joined in order to provide some sustainability and support to the project to ensure that it continues into the future. NumFOCUS provides educational programs and events, fiscal sponsorship, but more importantly, it provides resources to the project and a community. It forces us to think about things that we, until we became a member of NumFOCUS, we let slip through the cracks, like codes of conduct and diversity and other things. So this has been really fantastic. So we were chugging along for a number of years, developing PyMC3, when a series of unfortunate events occurred. In particular, one event in October of 2017, the Mila team, which developed the Theano project, decided it was time to discontinue the Theano project, citing the presence of other very well supported frameworks for doing deep learning. They had essentially decided that the utility of Theano had run its course, and that they were not prepared to continue supporting it indefinitely into the future. So Theano was to be no more. And this is, I guess, always the risk you run when relying heavily on another project. There's no guarantee that that project will continue indefinitely into the future. And so the Theano project was, not turned over to the open source community as we perhaps hoped it would. The project was closed, and we, at least at the time, really didn't have the appetite to maintain a deep learning backend. That was kind of out of the scope of our expertise. And so the hunt began for a new backend for what would presumably be the next major version of PyMC. And so we spent the better part of a year and a half evaluating all of these other computational backends that had come into play that were partly the reason for Theano's demise. So MXNet from Amazon, TensorFlow, PyTorch, and others. And we made the initial decision to try TensorFlow for a couple of reasons. One being that the TensorFlow project under Google had been extremely enthusiastic about PyMC3, trying to build on top of its platform. They were they helped us a lot in terms of resources and money to try to get this going. And also the development of a side project of TensorFlow called TensorFlow Probability, which included several components that were to be very useful in the development of any new version of PyMC. So data structures, again, like distributions, inference methods, MCMC inference methods, including nuts, and so on. And TensorFlow Probability kind of looked like this. Again, its heritage in deep learning. You sort of build a sequential model by adding distributions in the same way you would add layers to a deep learning model, and then you specify a log probability associated with your model and sample from it. And so we were what we sort of viewed our role as being a sort of high level front end to TensorFlow Probability that would perhaps be easier to use for a lot of applied users, similarly to what PyMC3 was doing for Theano. And at the same time that TensorFlow Probability was being developed, a brand new version of TensorFlow was also being rolled out. So in TensorFlow 1, you had a system that was based on building static graphs, much like Theano, and everything was executed in these sessions where the model was compiled and optimized and run. TensorFlow 2 was based instead on having a dynamic graph that had a much simpler end user facing API that evaluated models, what they call eagerly, essentially on the fly. And so you had an experience that was much closer to, say, what you would do building models in NumPy. So this presented challenges. Everything was changing very, very quickly. We went from a system, Theano, which essentially went unchanged for multiple years, to TensorFlow, which was changing, monthly or weekly. And again, Google was very generous with time and money. We had a couple of in-person developer summits where we tried to prototype what PyMC4 might look like, one in Montreal and one in London. And the challenge that we came up against when building on top of TensorFlow was that in PyMC3 we had this static graph that we were able to write things in a declarative way and then use the static computational graph to keep track of all of the dependencies. Here with a dynamic graph, we run into problems. There's really kind of two modes to any probabilistic program, where you build this graph, a simple version of which you see here on the right, that is meant to be run in two directions. So forward, from the sort of the top down here, we run from top to bottom when we're doing sampling, either in a prior or a posterior sense. And then we also have to run in a backwards sense for doing inference, where we start with the observations and we see essentially how those observations lead to more highly probable values for the unknown parameters. And so with the dynamic graph, it made it very difficult to keep track of the dependencies when we were calling things in the reverse mode. So we either had to keep track of this graph ourselves or write a function that could be reevaluated to make sure that we have the right dependencies. And the approach that ended up being adopted was the use of coroutines. And for those of you who are unfamiliar, coroutines are kind of like generators. They're sort of a complement to generators, except rather than producing values, they consume values. So in coroutines, the yield statement here appears on the right hand side, and it may or may not return a value. So in this case here, it's just a very trivial coroutine that when it's run, it essentially waits for a value to be sent to it by the send method, and then when it reaches the end, it stops. And what this allowed us to do was to do different things with our graph depending on which direction that we were running them. So the prototype that the PyMC4 developers came up with looked like this. So we were endeavoring to keep the user-facing API as close to PyMC3 as possible, except this time rather than a context manager, we had a function that was decorated with pm.model. So a decorator that essentially endowed it with TensorFlow probability niceties. And then each statement now is a coroutine. So we have equals yield instead of straight assignments that you see in PyMC3. So pretty good job. I mean, I think it's fairly concise. It's a little awkward having all of the yield statements, but it was, I think, the best that we could do given the constraints that TensorFlow probability forced on us. And there were advantages to having TensorFlow probability as a backend. Namely, it was really easy to generate multiple chains. And specifically, we can generate a PyMC4 model here and sample from it, and say just take 2 chains, and this particular model, the famous 8 schools model from Gelman et al. About 7 seconds to generate that. Let's say we want 128 chains. Well, we can get that same number, or perhaps thousands, in approximately the same time. So that there was a computational advantage perhaps in doing that, although each of these chains need to be trained independently and couldn't really share any training information. The other nice idea that was developed was the idea that every component of the model, each distribution, it in itself are models. So in this example here, this is the horseshoe prior, which essentially does L2 regularization in a Bayesian sense. This is kind of a custom prior distribution that essentially in itself is a model that gets embedded inside another model, in this case a linear regression. And we hope to continue using this moving forward, this idea. But it seemed like there were, in general, more obstacles than opportunities in using TensorFlow probability. It was as I tried to illustrate here, kind of difficult to develop on top of, at least relative to Theano, particularly as TensorFlow was changing so quickly. It was tough, really tough, replicating the PyMC3 user API. Again, I think a reasonable job was made of it, but not quite what we'd hoped. And the developers kind of voted with their feet. Over time, there was really little momentum from the PyMC team in continuing developing this. And really, a credit to the TensorFlow probability team, their own innovations were quickly making PyMC4 redundant, and a lot of these things, including the use of coroutines, started to appear in TensorFlow probability. So, as of kind of a month or so ago, the future of PyMC was really up in the air, there was kind of a half-hearted effort to continue developing PyMC4, but really a lot of the development work was still being put into PyMC3. And as things happen when you have a large and relatively diverse development team, people have good ideas, and talented people do talented things with code, and that was the case here. One of our core developers, Brandon Willard, who to this point had primarily been working on the symbolic PyMC project, which is in itself an interesting side project in the PyMC dev stable, came up with the idea of linking Theano to a different computational backend, namely the JAX backend. The idea here is that Theano, builds a static graph of what they call ops or operations that, in the context of a Bayesian model, represents the directed acyclic graph, and currently, in terms of PyMC3, it generates C code that's compiled for fast computation over the graph, but it's possible for it to be compiled to other backends. Currently, that's C and NumPy, and the C backend, which is more performant, is really the piece that we didn't want to maintain. We don't want to have to write code for TPU support and other innovations as they arise. But Theano supports linkers for converting graphs to executable functions, and it turns out that JAX has a identical API to NumPy. So Brandon had a go at this along with some of our other development team, and JAX, just for a brief introduction, is another Google project that was open sourced relatively recently, and it's described as a system for composable function transformations. What it really is a linear algebra accelerator, XLA, and Autograd. And from the standpoint of a probabilistic programming language, it really gives us the ingredients that we need for nuts, namely Autograd and linear algebra acceleration, without the constraints of a deep learning framework. So there isn't all of this other code that we would have to maintain and carry around. So perhaps Theano isn't dead yet, and it isn't. In fact, we forked the project. It's currently called Theano-PyMC, emphasizing the fact that it's being used exclusively here as a backend for PyMC and not for deep learning. This will probably be renamed sometime in the near future. And the idea is this, that we would be able to specify our models, continue to specify our models in PyMC3. So far, no changes would have to be made to existing PyMC3 models, perhaps arguments to sample, but nothing major. Then use JAX for the Theano backend. So here we see the piece that was written by Brandon and others. This is where the model is compiled to JAX. So all we have to do is write JAXified versions, if you like, of Theano ops. And because the API, again, is so similar to NumPy, it's relatively easy. And the result is a compiled JAX graph with no Theano PyMC3 code that can be run on any hardware automatically using any sampler that is implemented in JAX. This includes using TensorFlow Probability samplers. So TensorFlow now includes NumPy and JAX backends, or what they call substrates, that preserve the abstractions and API of TensorFlow Probability. And so the MCMC algorithms, which includes nuts, can be used to sample JAX compiled code. And so this takes full advantage of the JAX speedup that would otherwise require rewriting PyMC samplers in JAX. So it's important to note here that the TensorFlow Probability JAX backend does not depend on TensorFlow itself. And there are even NumPyro samplers working. And the performance right out of the box with, again, minimal amount of fuss, just a little interface for compiling to JAX is pretty remarkable. So here's the current benchmark for a simple model. This is just a simple hierarchical model, not important what it is. Built and run in approximately 7 minutes, but using sampling _ JAX instead of sample. The same model is run in 22 seconds. So it's quite an incredible speed up again, without any other optimizations going on. So this is kind of the idea here. We have our PyMC model that's, as before, turned into a Theano graph, but now it's being turned into a JAX executable that can be run under a variety of samplers. And of course, in our excitement of all of this, we posted, Thomas and others posted this example to Twitter, and one of the initial responses was, wait, you've got 4 or 5 frameworks here in 25 lines of code. Is this a benefit or a cost? Should I be excited or run? But it's early days. A lot of work has to be done, hiding a lot of this for most of the users and providing the high level API that we're used to in PyMC3. But before this, everything was a trade-off, and we don't have to make a lot of the trade-offs that we would have had to make adopting one of the other deep learning frameworks as our computational backend. So the future is very bright for PyMC, and now more than ever, this is the best time. If you're interested in contributing to PyMC, we need you, not just for the ongoing maintenance of PyMC3 or whatever it becomes, but specifically for the new Theano-PyMC backend. There's a lot of work to be done. Poor Brandon can't do it all himself. So we really implore you to join us, even if you don't feel confident yet tinkering with Theano. Testing, writing documentation, providing some of the changes that will have to be done to PyMC3 in order to do this. There are a lot of possible roles for you, and we welcome you into the PyMC world. So with that, I'd like to thank you. I hope that's giving you kind of an outline of where PyMC has come from and where we hope that it's going. More than that, I want to thank everyone that has ever contributed to PyMC, currently or in the past, in all versions. And thanks to the community, including those of you who use PyMC for real work. And of course, I want to thank the organizers of PyMCon 2020, specifically Raveen and Thomas, the executive chairs that really made this happen. All of the chairs and reviewers and committee members and volunteers. And of course, I really want to thank the speakers that have taken time out to share what they've done with PyMC during this meeting. I really hope the 2021 meeting will be in person. I'm getting a little weary of Zoom and YouTube talks, but this is definitely better than nothing, and arguably better in terms of reach. So please enjoy PyMCon 2020, and I look forward to talking to you in the live Q&A. Thanks very much.